circuit. Example. Use Kirchhoff's voltage law to determine the unknown voltage for the circuit. In this particular circuit, we have two voltage sources E1 and E2, and we have two loads R1 and R2. We know the voltage across E1 and E2, and we know the potential drop across R2. However, we don't know the potential drop across R1, which is V1. Now, using Kirchhoff's voltage law, that is KVL, we have to determine this unknown voltage. So, let us start from here. We are assuming that the current will travel in this direction. Hence, it is given that the polarity of V1 will have a positive sign on the left hand side and a negative sign on the right hand side. Now, applying KVL. Since we are moving from minus towards positive terminal, therefore E1 will have a positive sign in the equation, that is plus E1. Over here, as we are moving from the positive towards the negative terminal, therefore V1 will have a negative sign in the equation. Again, when we are moving from positive to negative, this will have a negative sign, that is minus V2. Over here, we are moving from positive towards negative. Again, this will be minus E2 and then equal to 0. That is plus E1 minus V1 minus V2 minus E2 will be equal to 0. This is the equation we have achieved through KVL. Now, if we substitute the values of E1, E2 and V2 in the equation, we can easily determine V1, which is 2.8 volt in this case. Voltage division in a series circuit. We know that according to Ohm's law, V equals to IR. That is, if I is constant, then V is directly proportional to R. Now, let us consider this circuit. Over here, we have three resistors, R1, R2 and R3. We can see that these three resistors are connected in series. Therefore, the total resistance of this circuit is RT, which is equal to R1 plus R2 plus R3. In this case, that will be 10 ohm. If we want to determine the source current, that is this current flowing through the source, coming out of the source and going to the load, then the source current will be equal to E by RT, which is 20 volt by 10 ohm equals 2 ampere. Now, if 2 ampere is the current flowing through all the resistors, then the potential drop across R1 will be 12 volt, across R2 will be 6 volt, and across R3 will be 2 volt. And the summation of the potential drops would be equal to E. So, you can see that if I is constant, then the potential drop across the load will depend on the value of the resistance. This is what the voltage division rule states. The voltage across a series resistive elements will divide as the magnitude of the voltage as the magnitude of the resistance levels. In other words, in a series resistive circuit, the larger the resistance, the more of the applied voltage it will capture. That is, the larger the resistance, the more applied voltage will be required for the current to flow. In addition, the ratio of the voltages across series resistors will be the same as the ratio of their resistance levels, which means that if R1 has a greater resistance compared to R2, then the potential drop across R1 will be greater than R2. Voltage divider rule. Let us consider this circuit over here in order to determine V1 and V2. So, in this circuit, as you can see, there is one source which is supplying a voltage of E volts, and there are two loads R1 and R2. we have to determine the voltage across R1, which is V1, and the voltage across R2, which is V2. So at first we need to determine the total resistance of the circuit in order to determine the current flowing through R1 and R2. Well, in this case, RT, which is the total resistance of the circuit, equals R1 plus R2, because R1 and R2 are connected in series. Now, IS, which is the current flowing through R1 and R2, can be written as IS equals I1, which is the current flowing through R1, and I1 is equal to I2, which is the current flowing through R2. That is equal to E by RT. Now, if we apply Ohm's law to each of the resistors, we can determine V1, which is equal to I1 R1, and V2 equals to I2 R2. However, we can also determine V1 and V2 in terms of E. We know that I1 is equals to E by RT. Now, if we substitute this variable over here, then the equation becomes V1 is equal to R1 multiplied by E divided by RT, and V2 equals R2 divided by RT times E. So basically the resulting format for V1 and V2 can be written as Vx equals Rx by RT times E. So the basic voltage divider rule states that the voltage across a resistor in a series circuit is equal to the value of that resistor times the total applied voltage divided by the total resistance of the series configuration. This will become much more clear when we do or solve a problem based on this. Example. These questions are based on this given circuit over here. We can see that there is one supply, our voltage source, which is providing a voltage E equals 64 volts, and there are two loads R1 and R2. R1 has a resistance of 20 ohm and R2 has a resistance of 60 ohm. And the polarity of V1 and V2 are given. Now, the question says, without making any calculations, how much larger would you expect the voltage across R2 to be compared to that across R1? Now, we have seen in the previous slides that the voltage in a series configuration, the voltage across resistors divide in relation or in proportion to the ratio of their resistances. Now, since the resistance of R2 is 3 times the resistance of R1, thus the voltage drop or potential drop across R2, which is V2, will be 3 times that of V1. Question 2. Find the voltage V1 using only the voltage divider rule. The voltage divider rule states that V1 equals R1 divided by RT into E. Now, we know R1 is 20 ohm and RT, which is the summation of R1 and R2, will be 80 ohm. So, 20 ohm divided by 80 ohm multiplied by 64. That would give you V1. So, V1 is basically equal to 16 volts. Using the conclusion of part A, determine the voltage across R2. In part A, we have stated that the voltage across R2 will be 3 times the voltage across R1. So, since we have already calculated the value of V1, which is 16 volt, therefore V2, which is the potential drop across R2, will be 3 times that of V1. So, 16 times 3 is equal to 48 volts. The fourth question states, use the voltage divider rule to determine the voltage across R2 and compare your answer to your conclusion in part C. So we have to again determine V2, but in this time we have to use the voltage divider rule. So the voltage divider rule states that V2 equals R2 divided by RT into E. So R2 is 60. RT is 80, that is 60 divided by 80 multiplied by 64 will also be equal to 48 volts. Therefore, the answer that we have obtained in part C is equal to the answer obtained in part D. Now, How does the sum of V1 and V2 compare to the applied voltage? V1 and V2 is added and that is equal to E. That is 16 plus 48 will be equal to 64 volt. This math has already been done over here. So if you have any confusion, please go through this slide very carefully. Parallel circuits. Well, as I have mentioned earlier that any two elements, if they have two common nodes between them, then those two elements are considered to be connected in parallel. When two resistors are connected in parallel, their total resistance is determined by the formula 1 by RT equals 1 by R1 plus 1 by R2. Rearranging the terms, we'll get RT, that is the total resistance, equals R1 R2 divided by R1 plus R2. Remember, this formula is applicable only when two parallel resistors are concerned. For greater number, for n number of resistors connected in parallel, we have to use the direct format, which is 1 by RT equals 1 by R1 plus 1 by R2 till 1 by Rn. For parallel resistors, the greatest current will exist in the branch with the least resistance. Obviously, if the branch has least amount of resistance, then more current will flow through that branch. Steps to follow while solving a circuit connected in parallel. As I have mentioned in the previous slides that in series configuration, the same current will flow through all the elements connected in series and their voltage or potential difference will vary based on the value of their resistances. However, in case of a